Hi all. In this class we can see what is the effect of temperature and doping on mobility of a semiconductor. So in previous class we studied what is the definition of this mobility. That means the mobility is defined as ease with which an electron drift in a material. So the ability to drift an electron in a material is called the mobility, or we can say that the mobility is a measure of how quickly an electron can move through a metal or semiconductor in presence of electric field. So the movement of this electron in presence of electric field is called as mobility. That means the easiness with which an electron drift in a material. So due to this electric field, the current due to this electric field is called as drift current, and the mobility is defined as the easiness with which an electron drift in a material. So we have two expression for this mobility, that is mu n is equal to qt by mn star, where mn star is the effective mass of electron and mu p is nothing but qt star by mp star. So in addition we can define this as on average drift velocity per unit electric field is also defined as mobility. That means negative of average drift velocity divided by electric field. So using this mobility we can write the conductivity expression for electron as sigma n equal to qn mu n, and for holes we can write it as sigma p equal to qp mu p. So due to this drift of electron and holes under electric field, the total current density due to drift is defined as q times of n mu n plus p mu p electric field, or conductivity into electric field. So that's called the Ohm's law. So the mobility of electron is represented as mu n and the mobility of holes is represented as mu p. Mobility of electron is qt star by mn star. Mobility of holes is qt star by mp star, and its unit is centimeter square per volt second. So these things we studied in previous class. In this class we are going to see what is the effect of temperature and doping on mobility. So in a semiconductor, both mobility and carrier concentration are temperature dependent. So in first module we studied how we can derive the expression for carrier concentration. So in that we studied that this N0 and P0, in that expression we can see that the N0 and P0 depend on temperature. Similarly, the mobility is also depend on temperature. There are two basic types of scattering mechanism that influence the mobility of electrons and holes, that is lattice scattering and impurity scattering. So this scattering is depend on temperature. So we can say that mobility is also depend on temperature in such a way that the mobility is depend on scattering mechanism and that scattering mechanism is depend on temperature. So there are two basic types of scattering mechanism that influence the mobility of electrons and holes. We have different types of scattering mechanisms are there, but in that the two basic types of scattering mechanism that influence both the mobility of electrons and holes. So we can see what are the different scattering mechanism that influence the mobility of electrons and holes. So scattering means the due to the lattice defect or due to the collision the electrons scattered. So that is called scattering. So first scattering is lattice scattering. So lattice scattering means a carrier moving through the crystal is scattered by a vibration of the lattice resulting from the temperature. So due to the temperature variation, the crystal undergoes some vibrations of, and due to this vibration the electrons or the carrier holes or the carriers will scattered. So that type of scattering is called as lattice scattering. That means the lattice scattering is due to the vibration of the lattice itself. So the vibration of lattice is caused by the temperature variation. The frequency of such scattering events increases as the temperature increases, since the thermal agitation of the lattice become greater. So if we are increasing the temperature, lattice scattering also increased. Therefore, we should expect the mobility to decrease as the sample is heated. So as we increase the temperature, scattering will increase, the lattice scattering will increase. Due to the scattering, we know that if the electron scattered, its mobility decreases. So the electron will move in a particular velocity, that is the drift velocity under electric field. In such conditions, if scattering occurs, its velocity or the mobility decreases. So we can say that the lattice scattering, that is due to the vibration of the lattice that is caused by the temperature variation. So the scattering events will increase as we increase the temperature. That means the mobility decrease as the sample is heated, or if we are increase the temperature, the mobility decrease due to lattice scattering. Next is the impurity scattering, that means scattering from crystal defects such as ionized impurities, and this type of scattering mechanism becomes predominant under low temperature. We know that the thermal motion of the charged particle is very slow, so the slowly moving particles may undergo more strong scattering. So we can say that the scattering causes decrease in mobility with decreasing temperature. So we know that under low temperature, the predominant scattering mechanism is impurity scattering, so the mobility decreased, and at high temperature, the scattering mechanism that will predominant scattering mechanism is lattice scattering, and also due to this lattice scattering, the mobility decreased. So we can approximate the temperature dependencies are T raised to minus 3/2 for lattice scattering and T raised to 3/2 for impurity scattering. So these are the two predominant mechanisms that cause the decrease in mobility. So if you have a different type of scattering events are there, then the total mobility due to this whole scattering is 1 by mu t is equal to 1 by mu 1 plus 1 by mu 2 plus 1 by mu 3. So this all the mobility due to the mobility decrement due to different scattering mechanism. So next we can see what is the total mobility. So here we can consider the total mobility is the sum of lattice scattering mobility and the impurity scattering mobility. So we can say that the total mobility 1 by mu is equal to 1 by mu L plus 1 by mu I, where mu L is the lattice scattering mobility and mu I is the impurity scattering mobility. So the main mainly the mobility depends on these two scattering mechanism. Then we can say that the probability of collision taking place in unit time, that is 1 by tau c, is the sum of probabilities of collision due to various scattering mechanism. So we are considering that scattering as lattice and impurity scattering. So we can say that 1 by tau c is equal to 1 by tau c lattice plus 1 by tau c of impurity. So the main thing is that the scattering is dependent on temperature, and this scattering is mainly reduce the mobility. So the two scattering mechanism that reduce the mobilities are impurity scattering and lattice scattering. Impurity scattering is dominant at low temperature and lattice scattering is dominant at high temperature. So we can see in figure the variation of mobility with temperature. So in x-axis we are taking temperature in Kelvin. So remember we are taking in log scale, and in y-axis our mobility, that also in log scale. Then we can say that at low temperature the predominant mechanism is the impurity scattering, and that is dependent on the temperature dependency of this impurity scattering is T raised to 3/2, and that of lattice scattering that will predominant at higher temperature, and that dependency is T raised to minus 3/2. So at low temperature as well as at high temperature the mobility is decreased due to this scattering. At low temperature the mobility decreased due to impurity scattering, and at high temperature the mobility decreased due to lattice scattering. So that's the figure variation of mobility with temperature. Next we can see the mobility effects due to doping, so or carrier concentration. So we can see that the mobility versus silicon, first figure showing the carrier concentration of silicon versus mobility, and the variation of mobility of gallium arsenide versus doping is given in second figure. So we can see that the mu p, mobility of holes is less than that of electrons in both cases, because the effective mass of electron is less compared to that of holes. That's why the mobility of electron is higher compared to that of holes. So mobility reaches a maximum value at low impurity concentration corresponding to the lattice scattering limitation. Both electron and hole mobilities decreases with increasing impurity concentration. Mobility of electron is greater than holes due to the smaller effective mass of electrons. So we can see in figures. So at low carrier concentration, that means at 10 raised to 14 or 10 raised to 15, we can have high mobility. So if you are increasing the carrier concentration, we can see at x-axis is the carrier concentration and y-axis is the mobility. So if you are increasing the carrier concentration, that mobility is decreasing. So we can say that at low impurity concentration, mobility reaches a maximum value, and if you are increasing the carrier concentration, this mobility decreases both for holes and electrons. And one more thing, we can see that the mobility of holes is less compared to the mobility of electrons. We can see that blue lines represent the mobility of electrons, and that black lines represent the mobility of holes. So in both for silicon as well as for gallium arsenide, mobility of electron is higher than that of holes. The reason is that the effective mass of the effective mass of electron is smaller compared to that of holes. Our mobility equation is Qt bar by Mn star. So the effective mass of electron is lower, so that is in denominator, so its mobility value become high. So that's the way the mobility is depend on carrier concentration. So we can summarize the mobility dependency of temperature and doping in such a way that the mobility is mainly depend on scattering, and that scattering we have two types: impurity scattering and lattice scattering. And the impurity scattering is predominant under low temperature, and the lattice scattering is predominant at higher temperature. So both at low temperature as well as higher temperature, the mobility decreased due to this scattering. And in case of doping, the mobilities have maximum value at low doping concentration, and if we are increasing the doping concentration, the mobility will decrease both for holes and electrons. And one more thing, the things we can see that the mobility of electron is higher than that of holes, because the effective mass of electron is less compared to that of holes.